In this video, we're going to learn about kinetic molecular theory, which is also described as KMT. So, kinetic molecular theory, or KMT, describes the behavior of gases in terms of particles in motion. It makes several assumptions about the size, motion, and energy of the gas particles, and essentially what we're going to be analyzing is kind of what's happening to the pressure inside a closed container when you change variables to a gas. We're going to go through a series of different molecular drawings to understand gas behavior in closed systems, and this part's important. All of these are for closed systems. So as we start to draw, we want to be able to differentiate between different substances. So right now we really don't know what helium or hydrogen are, but they are two different things. And so when we go to draw these, we want to make sure that we are differentiating between our helium atoms and our hydrogen atoms. So the way that we do that, we can change the shape. So we could do circles or triangles. We could change the size to show that we have two different substances, or we can change the coloration and the pattern that we're filling in. And by doing that, we can differentiate between all the different things we're trying to draw in these drawings. So for this one, it says draw a diagram that has 3 helium and 2 argon gas atoms. So there's a couple of things. We have 2 different substances. So maybe our first substance is going to be an open circle, and that's going to be my helium. And maybe our argon is going to be a shaded in circle. We have to make sure we have a key, because if you don't give me a key, I don't know what you're talking about. The other thing is that these are gases, so we're not going to lump them all at the bottom of the box. They're going to take the shape of the container, and they're going to be random, right? So we have helium, we have 3 of them. We have argon, 2 of those. And there's no rhyme or reason to where these are going into the box. They just are going to take the shape of the container. And then we don't know how fast or slow each are going, but we can go ahead and draw some arrows to show that we know that these molecules or these atoms are moving. So just as we talked about before, gas particles are in constant random motion. And we've seen this a little bit. Our arrows show how fast or slow the particles are moving. So not every particle has the same speed. It's the average, and that's why maybe this arrow is going to be a little bit shorter than this one. And if you're looking here, this is showing that that atom actually collided with the container. There is no rhyme or reason. There is no, you don't have to make sure that your lines are exactly the same length, because it's an average. Some are moving slower, some are moving faster, and we show that with, colliding into the container or shorter or longer arrows. We've talked about how we measure our pressure in ATM, and that's our force applied per unit area. So it's measuring the number of collisions. The more pressure we have, the more collisions we have. So we're going to be analyzing different scenarios that give us more collisions and therefore a greater pressure inside our container. So when we talk about how we want to change the pressure, we can change the pressure by changing the temperature, the number of particles, and the volume of the container. So if we want to increase the pressure, we're going to increase the temperature. That's going to make the molecules move faster. And if they're moving faster, there's more collisions with the container. We can increase the number of particles. The more particles we have inside the container, the more collisions we're going to have, the more pressure we're going to have. We can decrease the volume of the container by decreasing the space those molecules have to move. There's more collisions and a greater pressure. So let's go ahead and look at a scenario. It asks us to draw 3 atoms of helium in the first box and 4 atoms of helium in the second box. So the first thing we want to do is we want to go ahead and make a key. So I'm just going to do an open circle, and that's going to be my helium. And then both boxes have a temperature of 300 Kelvin. So I'm going to write that down here just so I know. This tells me that the atoms are going to be moving at about the same speed, so I need to make my arrows about the same size. So we have 3 atoms of helium. 1, 2, 3. Maybe some collisions. And then this one, we have 4. 1, 2, 3, 4. And again, we're going to make the arrows about the same. There's nothing noticeably different, really, between the two. Now we're going to look at these questions. It says, which box would there be more collisions between molecules? Well, let's look at it. Our temperature is the same. So that's not going to create any more or any less collisions. Our volume is the same in each, so that's not going to determine a greater pressure in either box. But box 1 has 3 helium atoms, and box 2 has 4 helium atoms. So box 2 actually has more atoms, which is going to create more collisions. So that's going to be box 2. And because box 2 has more collisions, box 2 is also going to have a greater pressure inside. One thing I want us just to be aware of is that we are going to call all of the collisions that are happening inside the container elastic, which means no kinetic energy is being lost. So in all of our examples, we're going to assume that there's elastic collisions, no kinetic energy is being lost when they collide with the container. Here's a quick real-world application. So if you are looking to be a respiratory therapist, they treat premature infants whose lungs have not developed. And what they do is they're providing aerosol medications. So there's tests that they can do that determine the oxygen and carbon dioxide levels in that patient's blood. And they're looking directly at how to get these gas particles into the lungs to help that child breathe a little bit better. We're going to go through a lot of examples of this in class. So if you have any questions, make sure you write it down, and then we'll talk about it when we see each other again.